NASA confirms 3I Atlas has shifted course. Avi Loeb hints at something engineered.
Deep space observatories detected something unprecedented racing toward our solar system at impossible speeds. Advanced quantum artificial intelligence systems immediately began analyzing the data, processing millions of calculations per second. What they discovered challenges everything scientists believed about interstellar objects. The readings show patterns that shouldn't exist in nature. Government agencies are scrambling to understand the implications. Multiple laboratories confirmed the same shocking results. But what happens when technology from another world arrives unannounced? Could we already be too late? The discovery that changed everything. On July 1st, 2025, something extraordinary happened that sent shockwaves through the scientific community. The Atlas survey in Chile detected an object screaming into our solar system at 130,000 miles per hour. Within hours, NASA released the discovery details, and what they found left even the most experienced astronomers double-checking their calculations. This wasn't just another space rock drifting through the cosmos. The object, now designated 3I/Atlas, was moving with purpose and precision that defied every model scientists had for natural interstellar visitors. Its path wasn't just fast, it was almost perfectly straight with an eccentricity over 6, setting a new record for any interstellar object ever recorded. But the real shock came when the first images arrived from NASA's telescopes. Instead of behaving like every other comet in recorded history, 3I Atlas was doing something that should be physically impossible. The object was displaying a plume pointing directly toward the sun, moving against the direction that solar radiation should be pushing any dust or debris. This wasn't a minor detail buried in technical reports. This became the headline of NASA's press conference, with veteran comet researcher Bryce Boland describing the phenomenon as completely unprecedented. The implications hit the scientific community like a thunderbolt. For decades, astronomers have understood that comet tails always point away from the sun, pushed by solar wind and radiation pressure. It's one of the most fundamental rules of how these objects behave in space. But here was 3I Atlas, brazenly breaking that rule and doing it in broad daylight, where every major telescope could witness the violation of cosmic physics, the physics-defying plume. When the Hubble Space Telescope locked onto 3I Atlas in late July, the high-resolution images brought the mystery into sharp focus. The plume wasn't trailing behind the object like a normal comet tail. Instead, it was pushing out from the sunlit face, stretching straight toward the sun in a way that made veteran astronomers question everything they thought they knew about how objects behave in space. The Gemini South Telescope in Chile and the Lowell Discovery Telescope in Arizona both confirmed the same impossible feature: a sunward plume that was persistent, bright, and visible in every single frame they captured. No matter what angle they observed from, or how long they exposed their sensors, the result was always the same. This object was somehow launching material directly into the solar wind. Think about it this way. Imagine trying to spit into a hurricane-force wind. The saliva would get blown right back into your face. That's exactly what should happen to any dust or gas coming off a comet near the sun. Solar radiation acts like a relentless wind, always blowing particles away from the sun. Every comet from Halley to the most distant visitors follows this rule without exception. But 3I Atlas was behaving like it had its own weather system. The dust appeared too heavy to be swept back by solar wind, yet too energetic to simply fall toward the sun under gravity. Astronomers ran dust dynamic simulations, adjusting for every possible variable they could think of: particle size, velocity, solar wind strength, magnetic fields. Nothing lined up with what they were observing. The only way to get material moving sunward with such persistence would be to launch it with enough force to overcome the push of sunlight itself. That requires a directed energy source, something actively pushing against the natural forces of space. Every other explanation scientists tried simply couldn't account for the shape and behavior of this mysterious plume, a chemical signature from another world. When the James Webb Space Telescope turned its powerful spectrograph toward 3I Atlas in early August, the results left even seasoned comet scientists staring at numbers they had never seen before. The main surprise was carbon dioxide, and there was a lot of it. The carbon dioxide to water ratio in the object's coma measured 8:1, with an uncertainty of plus or minus 1. To put this in perspective, most comets in our solar system carry a carbon dioxide to water ratio somewhere between 0.1 and 2. A handful might creep up to 4, but 3I Atlas sits 4 standard deviations above the normal solar system trend. Only one other comet in history has ever come close to this level, and it was considered a complete outlier. The Webb telescope team, led by Martin Cordner, confirmed the measurement using multiple spectral lines, mapping the coma at 3.3 astronomical units from the Sun. The carbon dioxide signature completely dwarfed the water signature, creating a chemical fingerprint unlike anything previously recorded. Even carbon monoxide, usually a strong player in distant comets, lagged behind at a ratio of 1.4 to water. But the chemical surprises didn't stop there. The Very Large Telescope in Chile picked up another anomaly that made scientists do double takes at their data. Atomic nickel was present in the coma with a production rate of 10 to the power of 22.67 atoms per second. That's an enormous number for a comet still well beyond Mars' orbit. Even stranger, the telescope team found no sign of iron vapor, which almost always appears alongside nickel in normal solar system comets. This combination of high nickel without iron, paired with the extreme carbon dioxide levels, painted a picture of an object that formed in conditions completely alien to our solar system. The chemistry suggested this visitor came from a stellar nursery with temperatures and pressures unlike anything that shaped the objects we're familiar with. Propulsion technology written in the stars. The more scientists analyzed 3I Atlas, the more its behavior resembled something they recognized from human technology. Ion drives work by pushing charged particles out of spacecraft using electric fields. There's no dramatic fireball like in science fiction movies, just a steady, focused stream that can accelerate a probe to incredible speeds over time. NASA's Dawn spacecraft used this exact method to reach the asteroids Vesta and Ceres. The exhaust trail from an ion engine is narrow, highly directed, and points exactly opposite the direction of travel. In the vacuum of space, there's no air to spread out the plume, so the ions shoot straight behind the spacecraft, leaving a faint but persistent trace. When researchers compared this to 3I Atlas, the resemblance became impossible to ignore. Instead of a sprawling tail blown around by solar wind like a typical comet, the material jetted out in a narrow sunward arc. The plume held its shape across weeks of observation, didn't fan out like normal comet dust, and seemed to actively resist the solar wind rather than being pushed around by it. Harvard astrophysicist Avi Loeb pointed out that if you wanted to slow down after a long interstellar journey, you would point your engines toward the sun and fire them during closest approach, using something called the Oberth effect to maximize your braking efficiency. This isn't science fiction speculation. Every major space agency uses the Oberth effect to plan efficient spacecraft maneuvers. The dust in 3I Atlas's plume wasn't the fine, fluffy material you'd expect from a normal comet tail. Instead, it was clumpier, heavier, and maintained its focus as it left the object's nucleus. The behavior matched what engineers would expect to see from a directed propulsion system rather than random outgassing from surface heating, measuring the impossible force. Astrometric teams at Lowell and Gemini South began tracking 3I Atlas's exact position within days of its discovery, creating a precise map of its movement through space. What they found challenged everything astronomers thought they knew about how natural objects move through the solar system. The standard approach involves fitting a gravity-only trajectory to the observational data, then checking for any unexplained deviation. Initially, the calculated path based on a hyperbolic orbit matched the early observations within expected error margins. But as July turned to August, something strange began to happen. The best fit solution started to drift away from reality. The differences between predicted and observed positions grew larger than the measurement uncertainties. By mid-August, the average deviation topped 0.7 arc-seconds, more than double what astronomers expected for such a bright and well-tracked object. More importantly, the deviations weren't random. They showed a consistent pattern, always shifting in the same direction as the mysterious plume. When the team ran a non-gravitational model, adding a small sun-directed acceleration term to their calculations, the fit improved dramatically. The best fit acceleration measured approximately 4 × 10 to the -7th meters per second squared, with an uncertainty of 1 × 10 to the -7th. That's a tiny force by everyday standards, but enough to shift the object's position by thousands of kilometers over just a few weeks. This level of precision in the measurements meant scientists could track not just the existence of the acceleration, but its exact direction and magnitude. The acceleration vector aligned almost perfectly with the axis of the plume, seen in telescope images. Multiple independent observatories confirmed the same pattern, removing any doubt about measurement errors or observational bias. Echoes of previous mysteries. The discovery of 3I Atlas brought back memories of another interstellar visitor that had puzzled scientists for years. In late 2017, astronomers at the Pan-STARRS Observatory tracked a fast-moving object tumbling through the inner solar system. That object, designated 1I Oumuamua, became the first confirmed interstellar visitor in human history. Oumuamua presented its own set of impossible characteristics. The object was small, with a brightness pattern suggesting an extremely elongated shape, spinning end over end every 7.3 hours. But the real puzzle came from careful tracking that showed it wasn't following a simple gravity-only path. There was a faint but steady acceleration, pushing it away from the sun. The acceleration measured about 5 × 10 to the -6 meters per second squared, exactly the kind of push you'd expect from gas escaping a comet's surface. But here was the problem. Telescopes found no tail, no visible coma, no dust cloud around the object. Even the most sensitive infrared observations turned up nothing. If there was gas escaping, it was completely invisible. This opened the door to extraordinary speculation. Avi Loeb argued that solar radiation pressure could explain the acceleration, but only if Oumuamua was extremely thin, perhaps just a few millimeters thick, like an artificial light sail. He published papers suggesting it could be a piece of alien technology, a fragment sent to explore other star systems. Most astronomers pushed back against this interpretation, proposing natural explanations like hydrogen ice sublimation or organic compounds that left no visible trace. But the debate never truly ended. Oumuamua became a touchstone, a reminder that interstellar visitors could surprise us, and that sometimes observational data simply doesn't fit into neat theoretical boxes. Now, with 3I Atlas displaying its own set of anomalies, the pattern becomes harder to dismiss. 2 interstellar objects, both showing unexplained accelerations, both defying standard models of how natural space debris should behave. The odds of this being mere coincidence are dropping with each new measurement. Statistical impossibilities pile up. Orbital dynamicists spent weeks crunching the numbers on 3I Atlas's trajectory, and what they found defied statistical probability. The odds of an interstellar object arriving on a path so closely aligned with Earth's orbital plane, tilted just 5 degrees from the ecliptic, came out to roughly 2 in 1,000. That's not just rare, it's nearly off the charts for random galactic debris. Most visitors from deep space cut through the solar system at steep angle, passing high above or far below the disk where planets orbit. But 3I Atlas slipped in almost parallel to this plane, moving retrograde in a path that seemed deliberately chosen. The trajectory wasn't just unusual in its angle. Computer simulations showed the object would pass within 29 million kilometers of Mars, then approach within 97 million kilometers of Venus, and finally swing within 54 million kilometers of Jupiter. Each of these close planetary encounters represents a statistical surprise on its own. Combined, the chance of a random interstellar object threading this particular sequence of planetary flybys drops to less than 1 in 20,000. These aren't numbers that happen by cosmic accident. The object's orbital eccentricity of 6.141 set yet another record. This value means 3I Atlas isn't just unbound from the sun's gravity, it's following a path so straight it barely curves as it whips through the solar system. Most interstellar objects have eccentricities just slightly over 1. This visitor's eccentricity is 6 times higher, slicing through space with almost surgical precision. For planetary defense teams monitoring potentially hazardous objects, these statistics raised uncomfortable questions. An object arriving this close to the ecliptic plane, moving retrograde, and targeting 3 major planets in sequence doesn't fit the profile of random debris. The alignment appears so deliberate that it challenges assumptions about how interstellar visitors should behave. The hidden maneuver window. On October 13, 2025, 3I Atlas will slip behind the sun, vanishing from every telescope on Earth for several critical weeks. This solar conjunction represents the ultimate blind spot in astronomical observation. No visible light can penetrate the sun's glare, no radar signals can reach past the solar plasma, and no instrument currently available can track what happens during this hidden window. The timing couldn't be more significant. This disappearance occurs precisely at perihelion, the moment when 3I Atlas reaches its closest approach to the sun. In the language of orbital mechanics, this is the point of maximum kinetic energy. The object will be moving at its fastest speed, experiencing the strongest gravitational forces, and any change in trajectory would have the greatest possible effect. For spacecraft engineers, perihelion represents the optimal moment for major maneuvers. The Oberth effect allows a well-timed engine burn to multiply changes in velocity, making this the most efficient point for acceleration or deceleration. If 3I Atlas were indeed under some form of guidance or control, this hidden window would provide the perfect opportunity for course corrections. The conjunction period lasts for weeks, during which absolutely anything could happen without human detection. An outburst of activity, a sudden trajectory change, a complete alteration in the object's behavior, all of these possibilities remain invisible behind the sun's overwhelming brightness. Previous comets have split apart, faded dramatically, or changed character entirely during solar conjunction, only to surprise astronomers when they emerged. Automated alert systems at NASA's Jet Propulsion Laboratory and the Vera Rubin Observatory have already flagged this period as a critical watch window. Mission planners are preparing follow-up observations for the moment 3I Atlas reappears on the far side of the sun. The data gap represents both a source of scientific frustration and a catalyst for intense speculation about what might occur during those hidden weeks. When 3I Atlas finally emerges from behind the sun, the world's most sophisticated tracking systems will be watching for even the smallest deviation from predicted behavior. Any sign that the trajectory has shifted, that the mysterious plume has evolved, or that the object's character has changed in some fundamental way will provide the next chapter in this unfolding cosmic mystery. Until then, the questions multiply while the answers remain hidden behind our nearest star. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content.